Hello, hello, good evening, sir. In this video, I am going to discuss about the part A of the assignment one, in which I have to. My objective was to identify the crystal point group of the given crystal you have provided us in the class, and I have to study about its morphology and explain why the crystal point group I have stated is the most probable one. So, before starting, I have taken some assumptions. While doing my observations, they were like the sides are taken as a smooth and are sharp. The opposite sides of hexagon are considered as equal because I have observed this property in many cases, but not in all. Means one to two, this was not resembled, so I have considered them as ideal. And the third assumption is like the crystals which have flat cross sections are ignored. I have considered them as faulty pieces and are broken in nature. So let's start with my observations. The first observation I made is like the crystal is of irregular hexagonal shape, which is cylindric, which means there is irregularity in the hexagonal shape. So there is not a chance of six-fold symmetry because although the opposite sides are of same length, but adjacent sides are of different length, and also the hexagonal shape was extruded, which means it was a it was a tall and cylinder appearance, and also the surfaces, the cross section surfaces were not flat. Instead, they were slightly tilted, which means there is a chance of monoclinic symmetry because in monoclinic symmetry, A not equals to B not equals to C, and one of the angle is also not equals to 90 degree. Uh, that's why I have made my as a probable probability that the most that the point group is the 2 by m, which clearly resembles the shape of the crystal you and it's of and it is reflects the shape of gypsum because the shape of gypsum is just like the same. And now moving towards the morphology of the crystal, it shows a twofold rotation axis, which means along one axis, if we rotate it by 180 degree, we will get the crystal back, and by the m, which means a mirror plane that's perpendicular to its twofold rotation axis. A mirror plane means that one side of the crystal is a mirror image of the other side across this plane, like here in this image. Although this image is not considered as it is, as the axis names might be different. So here, if I considered it the axis as A and rotate the crystal by 180 degree, I will get the crystal back, and taken a plane perpendicular to that axis means the and dividing the crystal into two parts, I will get the same crystal at the opposite side of the plane also. And talking about the talking about the higher order symmetries, I can say that the higher order symmetries are not available in this crystal because of this so cylinder length, because of the slant length at the cross section, which means one side is more lengthier than the other side, means which means the crystal is slightly tilted. That's why, because you can see this shape resembles the actual crystal shape in 2D. This length is lengthier, and this is little smaller. This destroys the higher order symmetries. Like in orthorhombic crystals, there is a chance of M symmetry, but that is not available here. there is a single axis here which about which there is a twofold rotation and a plane perpendicular to that which divides the crystal into two halves. Like if I can explain through a diagram, like there is this is a axis perpendicular to the screen, and there is a plane which is parallel to the screen. This plane, this axis about which if I rotate the crystal by 180 degree, the this crystal shape 2D, if I rotate it by 180 degree, I will get the crystal back resembling the same as before. And if I divide the crystal by this plane and see both side of the plane, I will get the same crystal, and which means it gets divided by it. And also it shows a inversion center, which means about that center, if I take the opposite side of that center, I will reassemble the same crystal. So I hope this was my this was my part A. And also, I have attached some references about from which I have which about which I have read about the morphology of a 2 by M crystal and gypsum shapes. And I hope you will be clear about my approach. So thank you. Now moving towards part 2. In the part B of the assignment, I have given a model CIF of BATIO3, and I have to construct these compounds using the Vesta software and constructing the CIF files. So moving to the Vesta software and starting from the telluride, starting from the calcium telluride, I have constructed it by editing the structure parameters here. As in calcium telluride, the calcium occupies the octahedral voids and the tellurium occupies the FCC lattice. So I have set it to I have set the coordinates here and set my occurrence as 1 and form the form the crystal by the set of the repeating unit. And for the unit cell parameter, like the lattice parameter here is I was given a 6.356. I've set it as it is, and the space group of this calcium tellurium is Fm minus 3m and resembles the cubic structure as all A equals to B equals to C, and each calcium atom is surrounded by 6 tellurium atoms, and each tellurium atom is surrounded by 6 calcium atoms, resulting in a 6 ratio 6 coordination. And now if I run this file, means it has run now, and the unit cell volume I have obtained is 256.7743.60. And now moving toward the second part, which is the gallium phosphide, which is of which the crystal is shown here. Here the gallium occupies the half of the tetrahedral voids and shows a zinc band structure. The phosphorus forms the FCC lattice. For this, the structure parameters are as given here. Yes, the gallium atoms are considered as 0.25, 0.25, 0.25, and the phosphorus at 0.00. And by unit translation, we will adjust all the positions. So otherwise, we can set occurrence as the number of atoms which we are required. Like in the FCC, there is a requirement of 14 atoms, like 8 at the vertices and 6 at the FCC points, face centered points. So 8 plus 16 is 14. So we can set the occurrence as 14 and we will get the same shape. And for the unit cell, here the lattice parameter is 5.448 and the space group is F minus 4 3m, and the system is also cubic here. So on running this file, the unit cell volume I have obtained is 161.700. So now the third part is the antifluoride structure of potassium oxide. So opening that file also. Yes, the file got run and the lattice parameter here is 6.449 and alpha equals to beta equals to gamma equals to 90 degree, which means this is also a cubic structure. And here the oxygen atoms form an FCC lattice and the potassium atoms occupy all the tetrahedral voids. Each oxygen atom is surrounded by 8k potassium atoms, while each potassium atom is surrounded by 4 oxygen atoms, resulting in a 8 ratio 4, which means 2 ratio 1 coordination. So here the lattice parameters are set as given, like yes, as potassium occupies the tetrahedral points, so 0.25, 0.25, 0.25, and oxygen occupies the FCC. That occupies FCC. That's why the shape is given here. And now moving towards the next, which is cellurium dioxide, which resembles a fluoride structure. So yes, the file got run and we have got this shape. This shows the cerium atoms form an FCC lattice and oxygen atoms occupy all tetrahedral sites. Each cerium atom is coordinated by 8 oxygen atoms and each oxygen atom is coordinated by 4 cerium atoms, leading to 8 ratio 4 coordination. So the previous one and this one also both have 8 ratio 4, which means 2 ratio 1 coordination. So going towards its structure parameters, the cerium here is a cation and is at the FCC. That's why there is a translation of 000, and we can set the occurrence as the number of required atoms. Like here for the FCC, we deal with 14 atoms, and the unit cell, the space group is Fm minus 3m, and the structure is also cubic here. So on running this file, we will get the same. And for the last part, which is the orange, which is the orange zinc, which has a cerium chloride structure, which means CSCl type structure. I can open this file like here. Yeah, as you can see, gold and zinc atoms occupy the simple cubic lattice and both body centered positions alternatively, means which means if we scale it to a larger one, we will see that the zinc also resembles a cubic structure, and the gold is also or here showing the same. The gold atom is at the center and the zinc at the edge, at the corners. So on finding out the structure parameters of it, yes, the zinc atoms here shown are plotted individually, and the gold atom is single and is stated at one at the body center, which is at 1 by 2 comma 1 by 2 comma 1 by 2, which is a octahedral void. Each gold atom is surrounded by 8 zinc atoms here, and each zinc atom is surrounded by 8 gold atoms. So which means this is a simple cubic one and and a 8 ratio 8 coordination, which means a 1 ratio 1 coordination. So in the third part C of the assignment, I have to make a presentation on the generation of X-rays based on the chapter 13, generation of X-rays of Girolami. So beginning with my PPT. Yes. The X-rays. Then, first of all, what is a X-ray? X-rays are generally a type of high-energy electromagnetic radiations with a short wavelengths that is ranging from 0.01 to 10 nanometers. Here is the range of different rays, but the wavelength which corresponds between 10 raised to minus 12 to 10 raised to minus 7 are generally considered as X-rays. They are produced when high energy electrons collide with a metal target, resulting in the emission of radiation. And also, the property of which X-rays follow is that X-rays travel in a straight line. So, now moving to the next page, the historical context means how the X-rays arises. X-rays was discovered by Wilhelm Conrad Roentgen in 1895. While studying the light given off during trap of certain substances in vacuum by cathode rays, he noticed that a piece of fluorescent paper kept very far away means that glowed when the tube was on. Although we know that the cathode rays do not travel much far, uh, but we have observed this property. So Roentgen stated those rays as X-rays. Principle of generating X-rays means what are the different principles which we can use for generate X-rays. The first principle is the electron acceleration and target interaction means that electron get accelerated in a X-ray tube or in a hot cathode tube and directed toward a metal target which converts kinetic energy to its X-ray photons, and this phenomenon we can state it as a white radiation. This is because of the continuous spectrum of energy. The minimum wavelength lambda minimum of the white radiation we can calculate by this formula of lambda min equals to hc by E max equals to hc by E times capital S, where capital S is the accelerating voltage. The light is emitted when charged particles change speed or direction. Means if there is a change in the particles movement, we will get the light. So the deaccelerated electrons radiate X-rays of various energies. So generation of X-rays by hot cathode tube. The hot filament that generates the electrons is negatively charged, which is the cathode, and the target is positively charged, which is the anode. When the electrons strike the target, X-rays are generated. The target will melt if the current striking the target is too large. Means we can't operate it on a large current. So to handle this scenario of large currents, we can use rotating anode, which allows use of larger electron currents and thus to generate brighter X-ray beam. In this design, the target is spinning metal ring, which means there is a spinning ring. There is a spinning ring which has a glass envelope, rotating anode, a slater, bearings, anode support, and rotor. So the struck section quickly rotates out of the beam, cooling down during each revolution. Means 3000 to 6000 revolutions per minute are done. And now moving to the next slide. The characteristics X-rays when incoming electrons knocks out inertial electrons means whenever external photon comes, the electron gets excited, and when it reverts back, it emits X-rays. This produces sharp peaks at specific energies independent of voltage unique to the target metal. The energy difference delta E between these two states leads to a characteristic wavelength which can be calculated by this formula of lambda characteristic equals to hc by delta E, and The third principle of generating X-rays is the Bremsstrahlung radiation, in which the electrons deaccelerate near the nuclei of target atoms, causing a broad spectrum of X-rays to be emitted, which is continuous in nature. Fourth one is the energy filtering and beam collimation, which means we can use the concepts of optics to focus the light rays and photons on a single point, so that more intensity can be transferred. So to this is was used to enhance intensity and direction, improving resolution and safety in imaging applications. So you can see the next slide. The synchrotron radiation. This is also a principle of generating X-rays. Synchrotrons are evacuated pipes curved into a large ring of tens to hundred of meters in diameter. You can see in this diagram. So one second. The radiated power P of a particle moving at relativistic speed in a circular path can be obtained by this formula, and the wavelength of the emitted radiation decreases as particle energy increases. Means how, as we know, the energy is inversely proportional to the lambda E equals to hc by lambda. And that's why the lambda is decreasing as the particle energy is increasing, creating broad spectrum useful for high resolution imaging and scientific research. Electrons are injected into the pipes and accelerated to very high speeds. Means from one side we inject the electrons and they are accelerated inside the ring at very high speeds. The selection of wavelength is useful in determining structure of protein crystals using multiple wavelength anomalous dispersion. So this one is also important for synchronous radiation. Like if we if we are able to select the wavelength, we can adjust accordingly as per the requirements. And now moving towards the type of different types of radiations in X-rays, we can find out KLM lines, and furthermore refer they are considered as characteristic radiations, and each letter specifies a electron shell. For the K lines, when which means from any shell n greater than 1, when the electrons revert back to n equals to 1, which and if it generates an X-ray, we will consider it as an n equal 1 line. The transitions in the K shell emits K alpha and K beta X-rays, and there is also probability of K gamma, which are high energy and short wavelength radiation lines. The K line's position is closest to the nucleus and at the n equals to 1 state, which can hold up to a maximum of 2 electrons. For the L lines, the L lines occurs when an electron from the L shell, which is n equals to 1, is ejected and an electron from the outer shell fills the vacancy. The transitions of L lines lower in energy K, such as L alpha and L beta, which means the electrons gets transited to n equals to 2 here, and the position of L lines is slightly farther from the K shell and can hold up to 8 electrons. So now for the M shell, which is n equals to 3, which means the electrons now stop at n equals to 3 shell. This has a lower energy than K and L lines, which means the energy release can be stated as the maximum in K shell, then lower in L shell, and the least in the M shell. And if we consider more, there is shown as 1, like there is an N, capital N alpha, we can make it further. but the energy gets so much lower that we can ignore higher terms. And for the position in M shell, they are the farther, and it can hold up to 18 electrons. The energy levels, the lower binding energy, it requires lower binding energy than K and L shells. So they have lower in energy but longer in wavelength, means their wavelength is higher. So the transitions in the M lines, they occur less frequently in traditional X-rays because they are of lesser energy. That's why we can see that there are some sharp peaks in K alpha and K beta just because of the characteristics X-rays and high energy of K lines. From this diagram also we can say that we can see different types of K values and different types of L values, which are K alpha, K beta, K gamma, L alpha and L beta. This were occurred by a incident photon, and when the electrons get ejected out, another electron from a higher state dip, gets into the K shell or the L shell or the M shell, generating X-rays. For the X-ray absorption, X-ray absorption occurs when X-rays pass through matter and interact with atoms, transferring their energy to the material. Key principles of X-ray absorption are totally dependent on photoelectric effect, which is the main phenomenon required for X-ray absorption. In this effect, an X-ray photon interacts with an electron in an atom, transferring all its energy to ej- eject the electron from its shell. And for the absorption edges, absorption is particularly high at specific photon energies called absorption edges, which correspond to the binding energies of the electrons in various atomic shells. And for the exponential decay, we can calculate the intensity of the decay of the intensity of X-ray by this formula of I equals to I naught e raised to minus mu x, which means there is a exponential decay in the intensity of the X-ray. The properties which are shown by X-ray absorption is as longer wavelengths are more strongly absorbed by crystals and give rise to diffraction patterns in which the beams are spread apart. The radiations emitted by hot cathode tubes is usually filtered to remove the K beta line. As the wavelengths become shorter, X-rays become more penetrating, meaning they are absorbed less and less strongly as they pass through a material. The percent absorption generally decreases as the wavelengths become smaller. This effect is shown by the curve here between 1.4 and 1.8. But as the wavelength continues to decrease, the X-ray eventually has an energy sufficient to knock electrons out of the K shell, known as the X-ray absorption edge or response resonance energy, where the absorption of X-rays increases as abruptly. You can see the absorption here is the maximum, and certainly it gets decreases. So this phenomenon of significant jump is shown by the absorption curve here. We can use this abrupt jump in absorption to create filters. So so for creating filters by absorption phenomenon, the absorption edge for nickel is for Z equals to 28 falls between the positions of the K alpha and K beta lines of copper Z equals to 29, which means the X-rays generated from a target with atomic number Z, a good filter to remove the K beta radiation selectively, is a foil with atomic number Z minus 1. So niobium Z equals to 41 is a good filter for K radiation from molybdenum. And for the practical implications of X-rays, we can say that each application of X-rays relies on the unique penetrating power, which means how much energy it can release, and energy characteristics of X-rays to provide invaluable insights in healthcare, security, research, and industry. Some major uses are like in medical imaging, like X-rays are typically used in creating images of the body and visualizing organs to check the faults in the different parts of the body. And second is the CT scans, which is the computed tomography scans. CT scans use X-rays to produce cross-sectional images, which helps in cancer diagnosis, stroke evolution, and internal injury assessment. The third one is radiation therapy in cancer treatment. High energy X-rays target and destroy cancer cells. Security and material inspection. Yes, it means while traveling, we have to go through checks which are done by X-rays, where the metal detection, etc., are taken place for the luggages. And the last part is the crystallography. The X-ray crystallography determines the structure of complex molecules such as the proteins essential for drug development and material science research. And the next one is thank you, sir. All my parts are done now, and I hope you will be fine with my understanding. Thank you.